Right, now we're looking for the pH of the acid before we even start the titration. And that's drastically different because it's nitrous acid. Nitrous acid means it comes from the nitrite ion. So before we even start, we have to realize that nitrous acid is HNO2. So that's what we're looking at, HNO2. Well, it's a weak acid. We've got it. We know it's a weak acid because we have its Ka value right here, and it is less than 1. So it's a weak acid. So when it's in solution, it's going to mix with the water, and it's going to hydrolyze. So we're going to add water to this, and it's going to hydrolyze, and it's going to make an equilibrium between NO2 minus, its conjugate base, and H3O plus. And that's what makes it acidic. That H3O plus is what makes this guy an acid. He can make H3O plus in water. But he's a weak acid. So we're not going to see all of these turn into NO2 minuses and H3O pluses. So this goes back to one of those simple ice tables we did in Unit 7. Unit 6, whatever unit was acids and bases. So I'm going to start out with my initial concentration, and again, some of you are going to be ready to skip this ice table. You're going to know this pattern by now, and it's 0.50 molar, and I don't have any NO, and I don't have any H3O plus. Well, as I go through my change, I'm going to lose some of him, a portion of him, a percentage of him based on that Ka value. A percentage of him is going to ionize, is going to turn into NO2 ions and H3O plus ions, but we don't know what that percentage is. So we just know we're going to gain X, some variable X. And then we'll know at equilibrium, we're going to have 0.50 minus X. We're going to have X, and we're going to have X. And we can set up our Ka expression using our reference packet, looking at what Ka is. In this particular example, Ka is 4.5. Again, it tells us, or we could look it up on our chart. 4.5 times 10 to the minus 4th. There's no units to K expressions. And that's going to equal X squared over 0.50. Now, my end thing here is pH. So I don't need to worry about these concentrations. I'm neglecting this X right here. I don't have to worry about coming back and plugging it back in because I just want to find pH. So this is the value I care about because pH comes from H3O plus ions. That's how we're able to solve what pH is. So this X is what's important to me. So before I finish this problem out, I'm going to write myself a note that I know X is H3O plus ions. So when I solve X on my calculator, I know that that's what I'm actually getting for that value. Again, if I wanted to know the concentration now of the nitric acid, I'd have to go back and subtract X. Just because I neglected it from this mathematical operation right here does not mean that that X did not play a role. Now, oftentimes when you go back to subtract it, because of significant figures, you'll get the exact same answer you started with. But when I solve for X, again, hopefully my calculations were right, I get 0.015. Meaning that only about 15 out of 25, what would that be, 30%. 30% of, oh no, not exactly quite a bit less than 30% from 0.5 to 0.01, only 1 out of 50, 2%, about 2%, 3% of the HNO3s turned into H3O pluses. And again, that would be an answer in molarity. And I just put a scribble there, but that's 0.015 molar. So to get its pH, I'm just going to take the negative log of the H3O plus concentration. So that's the negative log of that value. And because there's a 0 here, we should expect the pH to be something around 1, which isn't surprising. Even though it's a weak acid, it's only 10 to the minus 4. It's a decently strong weak acid. It's good at being a weak acid, better than most. And he's at a pretty high molarity, and we're dealing with quite a strong solution, 1/2 mole per liter. So at this point, I have got a pH of 1.82 when I do that calculation, and I would encourage you to do that calculation and check my calculation. But I shouldn't be surprised by that because I have a decently high molarity and a decently strong acid. Remember, pH is not a measure of whether or not you're a strong acid or a strong base. Your Ka expression would be. pH is a measure of how many H3O pluses are in solution, and there's 2 ways you can increase H3O pluses. one, add more of whatever the acid is. That's what we did here. Well, excuse me, I'm circling the wrong one. They're the same value, though. That's what we did here. Or you can pick an acid that ionizes better. Well, we have an acid that ionizes pretty good and a pretty high molarity, so we should expect a pretty low pH. Now, thinking about the graph at the back, I'm not going to do the graph as we go because it's just difficult to flip back and forth. But thinking about what that graph would look like, well, now I've got a point. I've got a point at my x value, or excuse me, my y value of pH is 1.82. My x value of volume, well, it's before the titration, so I've added 0 milliliters. So I've added not any NaOH, and my pH is starting off at 1.82. So I put a dot on the graph at that point.